and welcome to today's daily challenge. Let's begin our question. Okay, question 2187, the minimum time to complete trips. Okay, you're given an array of time where time I denotes the time taken by the ith bus to complete one trip. Each bus can make multiple trips successively. That is, the next trip can start immediately after completing the current trip. Also, each bus operates independently. That is, the trip of one bus do not influence the trip of any other bus. You're also given an integer total trips, which denotes the number of trips all buses should make in total. Return the minimum time required for all buses to complete at least total trips. Okay, so we're given an array of buses, essentially array that indicates how much time it requires a bus to complete a single trip. And we're also given an integer total trips, which we have to find how much time has to elapse. What is the minimum time that needs to elapse for collectively the buses to complete total number of trips? Okay, so an example is a time input array of 1, 2, 3, and a total trip of 5, and let's see, the output is 3. So just a little confusing of an explanation, but I think it's starting to make sense. So at time t1, the total number of trips completed by each bus are 1, 0, 0. The total number of trips is 1. T2, we have 2 trips completed because 2 divided by 1 is 2. 2 divided by 2 is 1. 2, 1. Sum is 3. And at T3, the total number of trips completed is 3 divided by 1 is 3. 3 divided by 2 is 1. The Pythonic or the computer way of dividing. And 3 divided by 3 is 1. Total number of trips completed is 3,115. So the minimum time needed for all the buses to complete is 5. Let's see, in here, okay, just a quick visualization of how this probably looks. Let's say 1. How would you display? Let's display the completion of a trip with a dot and a travel with a line down. So at T1, this is 0, or let's say T1. At T1, at T2, we have 1, 2, 0. At T3, we have 1, completed. And at this point, we can see that we have 1, 2, 3, 4, 5 dots. So, let's see. Time 1, time 2, time 3. Right? So, okay, right off the bat, what's the way to do this? We have a clock starting at 0, and while let's see, we'll also have a variable trips completed starting at 0, while trips completed is smaller than total trips, we would say that, let's see. So while we haven't reached our required total trips, we will iterate through the array of times. So for t in time, we will say trips completed plus or minus. Okay, and what are we actually doing here? At a certain time, the relationship between the times and the clock is per some unit of time. It takes some unit of time to travel for one bus, right? So for t, for each bus, and this could be time bus, it would take clock divided by t, the Pythonic way, of time elapsing to complete one trip. So this is essentially just trips completed, and we can return trips completed here. Also, we will be resetting this to 0 each time. And trips completed, sorry, we will be resetting, sorry, wait, is this correct? While clock plus equals 1, we have to return the time it takes for a trip to complete. So each time we're setting the, okay, yeah, this is right. Okay, wait, was that easy? Time limit exceeded. Okay, so this works besides for one issue. We are exceeding the time limit. Okay, let's draw another diagram. So our goal is 5, and if we do this a couple of more times, 4, 5, 6, 7, 8, we will see that this is essentially in line. And this is a okay, so what I'm trying to say here is that I'm trying to see if there's some faster way of, besides going through every single one. And unless there's some crazy math formula that I'm not aware about, another way that we could be looking at this is, let's say the goal is no longer 5, let's say it's 8 or something. Could we maybe like skip, or even better, not skip every other one, right? And thus dividing it by 2, but could we have a theoretical like min or low and then high set somewhere, and then basically do a binary search, right? Could we have a mid here in the case that the sum of, let's say 1, 2, 3, 4, 5, 6, 7, 8, let's say 9, right? In the case that we have 1, 2, 3, 4, 5, 6, 7, 8, we would set this to low, remove this, and then do this again. Call this mid, count how many trips have been done. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Too much. Then we would say high. Call this mid. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. High. And you see where this is going, right? Mid would now be low, and then we say 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we return time 5. I think that makes sense. Okay, so in that case, what is our we're still using the same okay, I have an idea. Let's turn this into a function. Let's have def trips in time. Here we're going to pass the clock that we defined earlier, and then simply say trips in time, trips is equal to 0. Trips completed. Trips completed is equal to 0. We don't need this guy here because we're only doing this once. While trips completed is less than, we don't even need this anymore. We're just going to say that for t in time, trips completed is going to be clock divided by t, and this is our little function. And let's now divide min time. What's our min time? Min time. What would be the minimum time possible for any trip to? So here, I guess min time isn't very important to set correctly right off the bat, but let's just call it min of the time array, and the high or max time could be, let's see, what is the maximum time that we know? Well, the max time, if we're given a goal of 9 trips, it would just be the 9 trips divided by the smallest element in the array. So that would be the, sorry, one more time. The goal, which is total trips divided by the min time. The minimum, let's just, for sake of m. Okay, and now we have to do a binary search, which works as follows. We have a max time, and we essentially just say that, let's see, we have to choose a mid time. Mid time is min time plus max time divided by 2. Sometimes this is hard to understand of why this works, but trust me, if you were to do it the way of max minus min divided by 2 plus min time, you would essentially just get this, right? So the other way to write this would be max time minus min time. So there you're getting like the range, and then you would say divided by 2, and then you would wrap this whole thing in parentheses. And since the offset was taken completely away, you would have to add plus min time again. But if you were to take off, this would be max time divided by max minus min time divided by 2 plus 2 times min time divided by 2, which just equals what I just wrote above here. So yeah, just please check that if you want. But let's see. Last part is, what do we do when we actually, so we have the trips, which is equal to trips in time given by mid time. And if, okay, so here's the tricky part here. If we're looking at mid and we're trying to have the minimum time, if we're trying to have the minimum time, minimum time to complete all the trips, in the case that we actually hit a, in the case, okay, so here's a tricky part. In the case that we hit the required number of trips, it doesn't guarantee us that, if we hit the number of required trips, it doesn't guarantee us that that is the minimum amount of time, because if this guy wasn't here, the smallest unit of measurement would no longer be 1, and we could be looking at a situation where mid, or the minimum amount of time is actually 1 prior to that, but we just would never know that because we hit the required goal and we exited out of the loop. So here I'm thinking that if trips, so we have to kind of look one ahead, and we can say if trips is less than, right? If less than total trips, then we're good. We're saying that if total trips, then yeah, then that's pretty easy. Max time, we know that it can't be mid time. But if, else, but if trips is greater than or equal to, so if our mid is greater than or equal to, if our, wait, hold on. Oh, greater than or equal to, sorry, what am I comparing again? I'm comparing the number of trips taken in a mid time. If a trips taken is smaller than the required, then we're setting the min time to the max time, to the +1. Else, if the trips taken is too much or even the same, then we say that max time is equal to min time and return min time. So this works. It does not. 3. What did I mess up here? What, okay, so let's just talk through. Okay, let's talk through the logic. We have a min a minimum time and a maximum time. Min-max shows the minimum amount of time potentially to reach some certain response, and a maximum time. I think the more important one is the maximum time. And why am I dividing? No, me dividing is just assuming I should be multiplying. I should be setting a higher threshold. And yeah, multiplying is the right thing to do. I don't know why I was dividing. Total number of trips is the um, total number of trips times the smallest. Okay, so let's think about how I'm doing this. Okay, I'm returning the completely wrong here. I don't know how I why would that? So one more time. Okay, hopefully this is correct. Oh, sweet. Okay, we have let's look at the answer. Okay, we're beating 81%. Yeah, I think this is pretty self-explanatory and it's really not worth going over. But, yeah, what is the thing to note here is that unless there was a clever math function that, let's see if there is actually. No, still binary search. Okay, and so if the best ones don't have a cool math formula to find the answer right away, then I don't think there actually is one. But the point here is, the idea is quite simple. We have a way to get the number of trips in a certain time. The function for that is pretty simple, and we've defined it even in the first iteration of the program, right? And then the approach here that we used to take is to just iteratively go through each single time slot and find if we have the correct time or not, right? And that is a O of n squared, where O of length of time times the total number of trips times the smallest element in that array. So basically O of n squared. What we're doing here is O log of n, because we're not going through each and every one. We're making log of n that comparisons, and that is done by binary search. So this is a binary search not over some data structure, but over the answers. And yeah, okay, on that note, I'm going to end the video, so thanks for watching. Feel free to use this solution. Thank you.